So there is something called law of the unconscious statistician. It's called notice. So what does it say? If x is a random variable, and g is a one-to-one function, it has to be one-to-one. Then the expectation of g of x, no, I'm not putting lowercase x, I'm actually putting an uppercase x, which simply means it is a random variable that is going to take all types of values from the support of x. That would simply be equal to all values of k in the support of x, g of k multiplied by the probability of x is equal to k. There's this true. Is x squared a one-to-one function? No, but if you restrict the domain, it will be one-to-one, correct? So in the problems that we are going to do, we are going to restrict the domain. So let's say you want to find expectation of x squared. Now, why do we need expectation of x squared? We need that to find the variance of a random variable. What is variance? Well, you should know this in 2023. By definition, the variance of x is simply the expectation of x squared minus the expectation of x whole squared. Where does this come from? Well, this is also how to say rationale. What does what does variation measure? Well, it is going to measure how far the data is spread apart, right? And we could simply do a range, right? Distance between point A, point B, but that's going to be, affected by skew and all. But if you remember how we calculated variance or standard deviation, we picked the average, yes, and we saw how far each observation was from the average, correct? And then we squared them because if I simply added them, it's going to become zero. Because some are above, some are below, so at the end of the day, it will be zero. So to avoid that, we square them. In simple terms, we are finding individual distances, taking the average of the distances to find the total net distance, right?
Just get rid of the negative sign.
Yes. So pretty much when I say an expected value of a random variable, I am doing expected value of x minus mu squared. Mu here is simply the expectation, the mean. So I'm starting the mean, looking at where each value is at. So I'm doing it for the entire random variable, all possible outcomes of random variable. So mu is simply the average, it is the expected value. Expected value is simply the theoretical average that we expect, hence the name expected value. I'm using mu so that I don't have to write expectation time and time again. If I FOIL, I would have x squared minus 2 mu x plus mu squared. Correct? Expectation is always found for a random variable. Are we clear? Because when we found the expectation, we looked at all possible values of x on the support of x, multiplied by its PMF, we got the expected value. But the moment you find the expected value, it doesn't have the random variable in it anymore. Do you agree? At least in the cases that we have seen. Yes? No, maybe. Go back and look at geometric. We had 1 minus b over p. Do you see anything random there? No. Negative binomial. R times 1 minus b over p. Anything random there? No. Binomial. N times p. N is a parameter, p is a parameter. Nothing random there. So, mu, once you find the expected value, is a constant. A simple, informal way to explain expected value of a constant C is just C. The simple explanation would be, well, expectation is always defined for a random variable, correct? Don't have a random variable, it's just a constant. So you get the constant back. But this can be shown easily by plugging it in the PMF or the definition of expectation. And you'll see the expectation of a constant is just a constant. I can use linearity of expectation and distribute the expectation. I have 2 mu x. We already addressed that mu is a constant, which would make 2 mu to be a constant. When we did the linearity of expectation, I mentioned that if we have a constant, we can pull it out of the expectation. So 2 mu, expectation of x. Last time I did write expectation of ax plus b1, correct? Or did I just do x plus 1? When I did linearity of expectation. So if we have a constant multiplied to a random variable, you can pull the constant out. This goes back to the same argument, the simple informal statement that I made. Expectation operates only on a random variable, not on a constant. So it will just come up. What is expectation of mu squared? Based on what I said about mu. Mu squared. What is the expectation of x? Mu. So we have expectation of x squared minus 2 mu squared plus mu squared, which will give us basic algebra. Minus mu squared, but we know mu is simply the expectation of x. So I can rewrite this as expectation of x squared minus expectation of x. 1. Good. Yes.
All right. Why do you use like brackets after that instead of parentheses?
See, I knew this was coming. It's just a habit of mine. When I do expectation, I put brackets. When I do variance, I put parentheses.
So it doesn't mean anything different?
No,
Okay.
it's just a habit of mine. So standard notation, most people would go with, expectation parentheses of x, variance parentheses of x. I always do it this way, but that's just me. So there is no difference between this and that. You can put brackets that too. Good. Now do you see where that formula comes from? Okay.
Why is it unconscious?
Huh?
Why
So you have to Google that. It relates to the history of the unconscious statistician. So I did read up on it. I just forgot the exact explanation.
We're also learning linear algebra about the theorem of socks and shoes. I'm sorry to get sick of these like silly names. Just tell me what it is.
Well, I do. I've read it before, but I just forgot the exact, context behind it.
I got the like gist of it, not the question of privacy
So you gotta take your sock, you gotta take your shoes off, and then you can take the socks off. Okay, and order of conditions, but.
So, yes.
I think it's called that because people tend to use the identity without realizing that it must be treated as the result of a rigorously proved theorem, not merely a definition.
Unconscious statistician, I did the exact same thing. Right, so now it makes perfect sense. Okay, Shay. So there is actually a short proof to that. I wanted to be unconscious, Jen. Sadly, I'm still alive.
Teaching by example.
What?
Teaching by example. It's method teaching.
There is a short proof and there is a detailed proof, but now it makes sense. Okay, we want to find the variance of a geometric distribution. We already know the expectation, correct? So the of x is 1 minus p divided by p goes back to how we define geometric. Right, that's how we define the geometric distribution. So now we've got to find variance. So in order to find the variance, I've got to find expectation of x squared. Yes. The law of the unconscious statistician simply states I could do k equals 0. I'm going to take individual values of k for x, right? So if you go back to the law, or notice, I wrote it as g of k for all k in the support of x. So I could simply rewrite x squared as k squared multiplied by probability of x is equal to k. Done. So k squared multiplied by the PMF, q raised k multiplied by p. P is a constant, so I can pull that out. So now we end up having k squared multiplied by q raised k. Agreed. How do we go about doing that? How did we find the expectation last time? For geometric, I mean. We're going to do the same thing. So yes. Now I'm going to take the first derivative on both sides. And that is going to give me derivative of q raised k is simply k multiplied by q raised k minus 1. What is the derivative on the other side?
Over 1 minus q squared.
Is that it? I forgot to write with respect to q. We're taking the derivative with respect to q. Is that it? Just 1 over 1 minus q squared?
There's a chain rule, but it doesn't cancel out.
So you have -1 and then negative from here, both would go away. Yes. So you will have 1 over 1 minus q squared. Well, great. I have k times q raised k minus 1. But I want k squared. What should I do? Abort mission.
Second derivative.
Take the derivative again. Nathan, why?
Because then you get k squared minus k times q k times k. And then you can just deal with the minus k part.
Yeah. So if I take the derivative one more time, k would simply become k multiplied by k minus 1, q raised k minus 2. We've got to take the derivative on that side also. So what is the derivative on that side? 2 divided by 1 minus q cubed. You do the chain rule, but the negative from the chain rule and the original negative would go away. So you have 2 divided by 1 minus q cubed. Going to keep this time. So I can pull over q squared, or q raised negative 2 out. That's what I meant by over q squared. I'll have k multiplied by k minus 1, q raised k. I know q is simply 1 minus p. So 2 divided by 1 minus 1 minus p cubed. I don't want to mess with the q's here yet. K squared minus k multiplied by q raised k. If I move that to the other side, I would simply have 2q squared divided by 1 minus 1, gone. Minus times minus b plus b, p cubed. Good so far? So summation k equals 0 to infinity, k squared multiplied by q raised k minus sum k equals 0 to infinity, k multiplied by q raised k would equal to 2q squared over p cubed. Good. Now, I can move that to the other side. Let's see if you can tell me what that second sum is.
Q.
What?
1 or q over 1 minus q squared.
Q over 1 minus p squared. I want an easier way. So when I do this trick, perhaps you can see where I'm going with this. What was that equal to? All I did is I multiplied and divided the second sum by p. P is a constant, so I have this. What was that equal to? Is it just the summation of the probabilities? It's getting closer.
Some sort of expectation.
It's not some sort of expectation. It is the expectation. Right? So that is the expectation of a geometric quantum variable, right? If you go back and look at how we started expectation last time, it was k multiplied by the PMF of geometric. That is the PMF of a geometric distribution. So that would simply reduce to the expectation . And we know what that is from last time. Good. Now I'm going to replace the Q by 1 minus B. What is, well, can I erase that sign? Yes. Multiply and divide by P. Good. Now I have P cubed in common. I have 1 minus P in common. Common denominator, P cubed, I pull that out. 1 minus P is in common, I pull that out. So I have 2 times 1 minus P plus P. What? 2, I'm putting 1 minus P.
In the brackets, the square parentheses.
What do you mean?
When you simplify that.
Oh, you're simplifying, okay. So 1 minus P over P cubed, 2, negative 2P plus P, 2 minus P. Are we done yet? That's just the expectation of x squared. Have to, I think it's a good point to mention here, x squared is the second moment of the random variable. So expectation of x squared is the second moment, which would mean expectation of x is the first moment. So we just found expectation of x squared. And we've got to do that. So 1 minus P.
I like to multiply by P as well, because the expectation is the sum goes from times P.
Here. Okay, so now expectation of x squared from over there is p multiplied by the sum k equals 0 to infinity, k squared q raised k. We found that sum, and that sum equals that. So 1 minus p over p cubed times p times 2 minus p. The p's will get cancelled. So we will have 1 minus p over p squared times 2 minus p. Good. Now we can plug it in the variance. So variance of x is expectation of x squared minus expectation of x whole squared. So that part, the second moment, we found that to be 1 minus p divided by p squared multiplied by 2 minus p minus 1 minus p over p squared. We know the expectation of a geometric random variable 1 minus p over p squared. So 1 minus p over p squared times 2 minus p minus 1 minus p squared over p squared. Going to erase this over here. What do we have in common? P squared, and what do we have in common there?
1 minus p.
1 minus p comes out, you have 2 minus p. And you have minus 1 minus p. Good. Two minus p minus 1 plus p. P's go away. 2 minus 1, 1. 1 times 1 minus p, 1 minus p, divided by p squared. So the expectation of a geometric is 1 minus p over p. The expectation of variance of geometric is 1 minus p over p squared. Okay, this is great and all. Did we find the expectation of a first success distribution?
This is just geometric.
Geometric, okay. What I did, an expectation problem.
Oh, wait, next.
Yeah.
Yeah, that was the one over p.
Yeah, so recall if y is a first success distribution with probability p, the expectation of that was 1 over p. I mean, if you have to take a wild guess, what would it be?
1 over p squared.
1 over p squared. Good. Okay. I don't have enough time to do this on. We will do that next time, but I'll end with properties of variance. Suppose C is a constant. What is the variance of C? 0. This is true for any random variable. You may wonder why expectations are important, expectations and variances. Sometimes you can find the distribution of some of random variables or difference or ratio, but sometimes we cannot. We just cannot come up with a distribution right away as a formula. That's when the mean and the standard deviation come into play, and we can use simulation techniques to computationally create a density for us. C is still a constant. Variance of C times X would simply be equal to C squared multiplied by the variance of X. C is still a constant. Variance of X plus C is equal to the variance of X. So intuitively, this should make sense, right? You're shifting every single observation by the same amount. So the variability has to be the same, right? That said, what is the variance of AX plus BY? Where X and Y are two random variables. A and B are two constants. I want you to take a guess.
Something like x squared plus 2xy plus y squared, but I don't know if it's constant.
Getting closer. So, what would the variance of AX be?
Is it the square root of the squares?
A squared variance of X, right? Plus B squared variance of Y. Now, this is the key part. We may or may not see this. Plus 2AB. COV stands for covariance. I think this comes later on. I'll do it now so you guys can get used to it. I'll just write the property, but the definition of covariance, we will do it when we have two random variables. So what does covariance mean? Covariance simply states how one random variable changes with respect to another random variable. With me? So it measures how one random variable changes with respect to another random variable. That said, if I told you that X and Y are independent random variables, what would that expression reduce to? Very good. Y and dy.
the covariance to be 0.
If two random variables are independent of each other, the covariance will be 0. Because if they don't have any connection, how could I say one variable is going to vary with another variable? So that would become 0, that would go away, and we would simply have a squared variance of x plus b squared variance of y. Good. Know these properties, they are very important.